Alright, so now we know what a vector valued function is from 12.1. What we'd like to do for the rest of the section, or rest of the chapter, is talk a little bit about what we can do with vector valued functions. So mostly this will involve taking derivatives and doing things with derivatives, and then the occasional integral. So before we talk about those, we just need to take a brief trip into 12.2, which is on limits and continuity. We'll say limits and continuity of vector valued functions, and we're not going to do much about this. This will be really brief, but just to sort of get it out of the way, so that when we talk about derivatives, I can make a side note so we really understand what's going on. So I'm going to list these as just two basic facts. We'll look at two examples. So first fact is we'll say the limit of a vector valued function. Say can be defined by taking the limits of the component functions. So let's just look at two examples. So suppose, for example, we took the limit as t approaches, say, 1, and so we'll have a vector valued function in here, something like t squared I plus 2tj plus 1 over tk. Right, each of those individual functions, let me underline them here, the t squared, the 2t, and the 1 over t, those are continuous at t equals 1, which means we can just plug these in. So this becomes 1i plus 2j plus 1 over 1 is 1k, and that's it. So we just took three individual limits. Or if we had something like limit as t goes to 0, let's say sine t over ti plus tj plus e to the t plus 1k. That first limit, the sine t over t, this is a limit you may remember from Calc 1. Then we have a t here and e to the t plus 1 here. Those second two are continuous. So the limit as t goes to 0, sine t over t is 1 I plus 0j plus e to the 1 is ek. And of course, the limit, in order for the limit of the vector valued function to exist, all three have to exist. So if we had something like the limit as t goes to 0, say 1 over ti plus t cubed k, or j, let's say, minus tk. That first limit, that first component right there, the 1 over t, as t goes to 0, that's undefined. So this whole thing is undefined. This is again because the limit as t goes to 0 of 1 over t is undefined. So don't worry if you're concerned that you have to remember all the limit rules from Calculus 1, Calculus 2. You don't. Like I said, I'm sort of covering this as a matter of course, so when we talk about derivatives, I can make a basic statement, but really we don't need to worry too much about this stuff. And then the related fact, because it's technical, and if you're an engineering major, physics major, you don't need to necessarily know the technical details in depth. And if you're a math major, you'll see all these again in all the gory details when you get to advanced calculus. So the second fact is a vector valued function is continuous at a point. That means at a t value. Right? If and only if all the component functions are. So for example, something like, say, if we write down a vector valued function, f of t equals, say, t squared I, let me make sure we have an I in there, plus 2tj plus 1 over tk. This is continuous. At t equals, say, 3, because each of the 3 is each of t squared 2t, and 1 over t is continuous at t equals t. Whereas, for example, something like, say, g of t equals, say, e to the ti plus 1 over tj plus, say, tangent of tk. This is not continuous at, say, t equals 0, because 1 over t is not. And, for example, it's also not continuous at, say, t equals pi over 2, because tangent of t isn't. So these are sort of small points, but keep them in mind. So when we talk about derivatives, like I said, I'll be able to make one statement related to limits, but otherwise just think these things are true if they're true of the component functions, and that's all we really need to worry about. And we'll see a bit more about it later. But really, that's the end. That's the quickest section in the chapter, 12.2. So let me close that up, and then we can move on to 12.3, talk about derivatives.